Hello. This is the continuation of our CS330 linked list review 1 example set discussion. Now this is picking up with example 4 right here. Now we've already discussed example 4. We went through that in the previous part of this lecture. But I want to revisit it real quickly in one specific context. I want to think about linked lists a little bit more carefully. Specifically, why we use linked lists and the penalty that comes with it. The memory penalty, memory access time, and all this stuff. Now, if we dig through this linked list code and we look at it, in this code right here, every time I want to add a new node, I'm calling this append node function to make a copy of that data. If we jump down to append node or prepend node, they would both end up resulting in the same overhead. If we look at this, I create one new node somewhere in memory. Well, I create a pointer so I can reference it. Then a couple lines down, I actually allocate that new node somewhere in memory. And then, after adding the first node, every other time I call this function after that first node, I am linking this node that's somewhere random in memory to whatever node came before it. So what I want to do is I want to go ahead and switch over to my document camera here. So I'll just draw a picture of what actually kind of happens here. So I'm going to draw in red what we actually have happening here. So right now, let's say that this is our first node. Now, traditionally, we're used to drawing linked lists sort of linearly like this form right there. This is how we're used to drawing linked lists. But we know that that's not what actually happens in memory. They're not linear in memory like that. If we look at memory as sort of this big 2D box right there. If we look at memory as sort of this 2D abstract box representing memory on your computer, what we will end up having is we'll have the first node maybe here, which points to the second node, which is maybe over there, which points to the third node that maybe is somewhere over here, which points to the fourth node, which is there, which points all the way over here to this other node. What we really end up with is something that looks much more like this in memory, just nodes scattered throughout. And this is why we don't always just say use a linked list. This is why we don't always just default to a linked list. Sometimes we use arrays. Sometimes the overhead of resizing an array is better than the overhead of jumping all over memory every time we need to traverse a linked list. And there are a few tricks to mitigate this. What you end up doing, one of the tricks to mitigate this is what is based around something called memory pools. And basically what you do is you say, I know I'm going to allocate one node. But instead of allocating one node, I'm going to allocate a block of nodes. I'm going to say, well, if I need one node, why don't I just go ahead and allocate the next 2, 3, 4, 5, 6, 7, 8. So every time I need to allocate a new node, I'm just going to allocate a block of 8 in total. And then I'm going to say, okay, I'm going to go ahead and use this node. And then the next time I need a node, I'm just going to pick up this guy. The next time I need a node, I'll pick up the next one, 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 the next one. And then when I run out of memory, I'll say, well, I'll just go ahead and create another block of 8. And then another block of 8. And then another block of 8. So I sort of start mitigating. I start mitigating this overhead of allocating a bunch of single individual nodes. I mitigate this overhead of jumping around through memory, and I can get a little bit of a performance increase there. Now, talking about how to measure this performance and everything, that's outside the scope of this course. But at the end of the day, what this really boils down to is if we have a linked list and we want to mitigate this overhead and allocate a block of nodes, there are two ways of doing that. The sloppy way and the way that follows separation of concerns, the way that follows that S in solid. And that's what we would really, really like to do. So now I'm going to go and switch back to my editor right there. And what I want you to do is I want you to look at this code very, very carefully. And we want to focus on a few pieces of code. We want to focus on how I allocate a new node. Then we want to focus on how I copy a bunch of nodes, where the copy logic actually happens. And what we're going to see in example 5 and then example 6 is a few changes. One of those changes can be fairly benign. Instead of you saying new node, I'm going to do something else. Right? Instead of saying allocate a new node. I'm going to change this line to call a function that actually allocates things. So it's going to be a quick one-line change for that. But where the bigger change, the less obvious change is going to come into play is in the copy constructor. Once I start implementing this memory pool logic, the copy constructor is going to change. Example 5 is going to be a very, very sloppy, quick and dirty implementation of a very, very crude memory pool. And I want to emphasize that. Example 5 is the quick and dirty, hey, let's throw in a memory pool, just start visualizing and playing with it. Example 5 is probably the absolute worst way to implement a memory pool in any capacity. Go ahead and switch into example 5, which is the actual first example we want to discuss here. Let's change it to that source directory. And if we look at this, I did collect some stats. Right there. I did collect some stats on memory and all that stuff. I used the time command embedded in the Zis shell. And I said allocate 8,192 block of memory pool. Basically, I said, you know what? I want a memory pool, so I'm going to allocate a really big array of 8,192 nodes. Now, why 8,192? Because that's the biggest array I could allocate on Atria when I was playing with testing this code here for this demonstration. Anything above 8,192, I get a memory fault, seg fault. But once again, example 5 is probably the worst way to implement a memory pool. It's the most quick and dirty way of doing it. It's the absolute worst way. And it only does it in one place. So let's take a look at that right here. So, you'll notice that I got rid of everything. There is no more linklist.h and linklist.cpp. This is now a proper template. So I said, you know what? Why am I building a linked list of integers? That makes no sense. Right? Why would I implement a linked list for integers, a linked list for characters, a linked list for chars, a linked list for doubles? Why would I do all of that when I could use a template to say, here's linked list code. If I want integers, I can get that. If I want doubles, I can get that. If I want strings, I can get that. And that's what this allows me to do. So I'm going to use a template. I've turned our integer linked list into a generalized templated linked list. So that changes our node slightly. But our node right now, instead of having the type be int, the type is now a placeholder t, our template parameter there. And in this context right here for this code right now, type name and class are equivalent. Now the answer to the question, are type name and class equivalent within templates in general? That's a much more complicated discussion due to some differences between C++11, 14, 17, and 20. But in this context, type name and class are equivalent. But my node stores data, and that data can be an int, it can be a string, it can be a char. This code will allow me to create a linked list of integers, chars, strings, or even other linked lists if I were so inclined. Now I have created a node constructor, and you will see here that I no longer have a node default constructor. I have now compressed them down into one thing. I'm saying by default, D gets whatever 0 value is appropriate. So right now, I am sort of faking generalizing it because setting D equals 0 does change a few. But right now, if I do not supply an argument for D, it will just default to 0. And then next is going to be null pointer. But this is our node right there. Now, right here down there after node, I have some boilerplate template code for setting up an iterator. I'm going to table that discussion for now. I'm going to leave discussing iterators to when we start discussing example 6, and we'll focus on it there. But what this really boils down to is giving me the same ability to use find, find if, sort, and the same while iterator loops you see people using with standard vector and standard list. This is some of the boilerplate code I need to make that happen with my own data structures. But I think we can ignore this for example 5. We're going to table this discussion for the moment, and we will discuss this in more detail during example 6. But what I want you to keep in mind, especially during this discussion right here, is this discussion is focusing on the things we can do if we're careful in our design, the things we can do and the tricks we can employ once we get through the next few weeks. So this discussion is really sort of examples 5 and 6 are, yes, things you need to know, but they're not things you need to know just yet. They're things you need to know exist. But after the next 2.5 weeks, after working through the review 2 examples and the review 3 examples, this stuff will start falling into place a little bit more readily. Right now, I'm really just focused on looking ahead and seeing what is possible, showing you what we'll be able to do over the next few weeks. So I'm going to skip over this iterator code. I'm going to make one quick note. These are known as type aliases. They are a newer version of an older mechanic called type defs. So I'm going to go ahead and prefer type aliases over type defs. Then we get down to the rest of our linked list code, and this is the stuff that should be familiar. You can see I've cleaned up the documentation here. I'm documenting these a little bit more explicitly. Right, we have the head pointer to the beginning of our linked list, just like before. We have a tail pointer to the end of our linked list, just like before. And now I've changed the name of my counter to be probably a much more elegant, much more self-documenting. Current size. The current size of my linked list. It's self-documenting. I know what it captures, and I can infer its type from its name. If I'm just reading through the... Nice. The first thing I'm going to do is, well, you know what? Let's rename things, right? During my earlier discussions, I said I called the append node function append node for the sake of discussion. I'm going to go ahead and change the name of my append node function to pushback. The name of my append node function is now pushback. Why? Well, why not? Pushback is the name standard vector uses. Pushback is the name standard list uses. If pushback is the standard name in the C++ language for adding to the end of a data structure, let's go ahead and mirror that with our own code. And because I have iterators, I can use a range-based for loop, which is very, very nice. But basically, this handles all the boilerplate for working with iterators. What this loop does is it takes all the boilerplate for taking an iterator, doing all the arithmetic, making all the calls. It takes all that boilerplate that I would have to write doing something like this. Right, instead of writing this while loop right there, I can now use a quick one-line iteration loop. Right, the first line, this sets it up. The compiler will generate the increment steps. The compiler will generate the initialization steps. The compiler will add the stop condition. We're going to talk more about range-based for loops over the next few weeks. But just appreciate that this gets rid of all the boilerplate you would normally have to write. But you have to write different boilerplate to make. Think about this. Now, the third option, after we get through that, is to say, well, instead of doing option 2, if we were to do option 3, this is when we could start playing with a memory pool right here. And you can see there is a lot of pointer shenanigans happening here, right? So the first thing at the very top is current size equals source.current size. So ignore option 2 and pretend option 3 is the sum total of this function. The first thing I need to do is know what the size of my linked list needs to be. Then I'm going to go ahead and allocate a temporary array of nodes. And so I'm going to create a pointer to an array of nodes. So create a new array of current size. I need to determine the last index in that array, right? If my array has a size of 10, my last index is 9. Or if my array has a size of 25, my last index would be 24. I'm then going to use the address of operator. So I'm going to say the head of my list is going to be the very beginning of that array. So I'm going to go to the beginning of my temporary pool array, go to the very first element, element 0, and get its memory address. In this context, the ampersand is the address of operator. Get the address of that variable. Where in memory is that variable located? Then same thing. Because I know the size of my array and how many nodes I will need, I need to get the address of the last node in that array. And that will be the end of my list. And then I need to iterate over my original linked list. And in this case, I can guarantee that both my linked lists are contiguous blocks of memory because of the setup I've done here. Now I run into the case of, well, I need to go through my array, and I need to set up the links. I need to go ahead and say, first thing, go through this array, and set up all the next pointers. Basically, just go through the array and say element 0 points to element 1 points to element 2 points to element 3, so on and so forth. And then the second thing I need to do is grab the data from the source linked list. Use the same source iterator. So what I end up having here is two interleaved loops. I have the for loop I would have to write to iterate over this array I've created, and I have sort of an embedded while loop that's happening at the same time to iterate over the original linked list. And then, of course, because I'm iterating over the original linked list, I need to move forward one. And then I need to handle the last node in a special way, right? In this case, you can see I'm stopping just before the last index. So if I have 10 nodes I need to copy, this loop will only run over the first 8. Excuse me, if I have 10 nodes I need to copy, this will only iterate over the first 9 nodes, 0 through 8. The 9th node, the last node, is handled right here, right? The last node is going to point to null pointer, but I still need to copy the data into it. Then that handles that right there. But as you can see right here, I am starting to add memory management logic to my linked list. And this is starting to get messy, right? I'm starting to do data, memory allocation, memory copies. And I have this giant block of code right here. And despite the fact that it does the copy for certain size linked lists, if I want to do anything more complicated like this, if I want to start doing multiple blocks of nodes instead of just one big one, this code is going to become unmanageable, right? I want to keep my memory allocation logic separate. Now, there's something called move semantics, which are very, very interesting. It's basically saying, handling the case where you're returning something that's going to be immediately reassigned to something else and disappear. We'll talk about this later in the semester, but this is a quick draft implementation for what we might do with a linked list. And then deallocation remains the same. And then you can see all I've done is renamed append node to pushback. And I got rid of most of the comments here. I got rid of most of the comments, and I cleaned this up a little bit. I'm using the standard return trick right here. Right, one of the nice things about return is as soon as we encounter a return line in a function, we know that function terminates. So right here I'm saying, if I'm adding the first node, do this, stop, do nothing else. But the second and third time I call it, all of this will occur. And the benefit of this is I don't have the else block underneath. I don't have that extra block of indented code. And I sort of clean up the conditional blocks. I sort of clean up the readability of the code a little. And then I have some iterator stuff I've thrown in there. And now I do want to emphasize, I am skipping over a lot of this iterator stuff because right now it is mostly just looking ahead at what we're going to do in reviews 2 and 3. Iterators are something that are technically beyond the scope of this current discussion, but the purposes of review on examples 5 and 6 are in showing you what is possible and in showing you what we'll be discussing over the next few weeks and what we'll be able to do after the next. Then we have some stuff here, just standard move assignment operator. The big thing you can see I've done here is I've changed from using an integer for my size to returning size t, which we can just go ahead and do some hand waving and say is an unsigned int, meaning an integer we always know is positive. Once again, a little bit of hand wave. But example 5 should motivate at least one thing, and that one thing is really, I have memory management logic. What am I doing with that? Where is that happening? It becomes very, very messy. Right? I have the linked list data structure logic of adding new data, moving through that data, iterating over it, copying it. But allocation is more complicated than simply saying new. Instead of saying, I want one new node, I want the block of nodes. And when I allocate a block of nodes, there is some linking I have to do. There is some non-trivial logic. And this is just a simple CRUD implementation. Right? If we run this right there, and we create a block of nodes here, let's say I'd want to do 100 right there. Point is, as soon as I run this, things start getting really, really messy. So running this, we can see it still runs. It still gives us the same results, copy, and all of that. But the memory allocation logic, just to do a simple array block approach, a very, very crude approach to allocating multiple nodes simultaneously, the code has become difficult to organize. Right, we're starting to get into the point where we need to figure out how to handle memory allocation logic, where it goes, and everything. We're getting very, very dangerously close to violating the essence solid, separation of concerns, single responsibility principle. And that's what brings us to example 6. Now in example 6, I'm going to add a source file. We still have linked list, but I've added this new naive pool.h function. Well, excuse me, header file. And it is, once again, templated. So just like the linked list is templated, our memory pool is also templated. Now, once again, I want to remind you, this is a sort of looking forward. This is sort of a topics of interest type lecture. You don't need to understand all of this just yet. You don't need to understand this in detail just yet. I want to show you that if we follow these notions of separation of concerns, the essence solid, we separate out the logic that handles specific things and we organize things and we're careful, we end up with a manageable code base where we have some flexibility. And more importantly, we can keep track of what happens where in our code. So if we go into the linked list, we'll see that there is still a node struct. That's still there. It's still private. And you can see that I've gone ahead and separated out the two node constructors right there. I've cleaned that up a little bit, right? I said, let's just go back to using the old school default constructor. Let's let an implicit call happen to the default constructor for whatever our data is. So let's let tData call the appropriate default constructor. If it's something like an int, we'll zero it out manually later. And then I have my non-default constructor so I can pass in a specific set of data. But I've separated that out. I've cleaned it up. I'm going to skip over the iterator discussion for now because that'll be a major discussion in Review 3. Talking about iterators and the template trickery and the template tricks I'm using here, that's a discussion in its own right. And that is a discussion I am going to postpone until a couple more example sets later. Until we reach Review 3. The end of Review 2, the beginning of Review 3. This is just something we want to defer until then, until we have seen a little bit more code, organized a few more things. Iterators are really things we need to start adding in after we've talked about the rest of the C++ class checklist, the big three, and all of that. Until we have that solid foundation, talking about these iterator and template shenanigans, that's going to result in probably a little bit more confusion than we want at this point. But this is a very, very important trick to add. The iterators are very, very important. But let's make sure we have a strong foundation in the fundamentals before we move on to implementing iterators. Even more importantly, implementing iterators with template trickery, template magic, template mechanics. But we can see I'm adding something now. Now I still have my 3 pieces of data from before. I still have my head pointer. I still have my tail pointer, and I still have my current size counter. But now I have this new node pool type. So this is an alias, so I'm saying anywhere I type node pool, anywhere I type the word node pool, it is simply going to expand out to naive pool bracket node. So instead of typing naive pool bracket node everywhere, I just want to be able to type the shorter node pool, a pool of linked list nodes. So that's my type def, my type alias. And down here this is the memory pool that handles all logic. This is where all memory allocation happens. So I'm not going to call new and I'm not going to call delete manually anymore. Not from linked list at least. All of that logic is going to be encapsulated into this memory pool. Now I do want to make a quick note. This naive pool I'm talking about does mirror the C++ allocator pattern. It mirrors the pattern. It is not equivalent to it, and it does not apply it. But this notion, the way I'm using a memory pool here, this naive pool, does mirror how allocators are used in standard vector and standard list. And once again, that's mirror. I'm not saying it's equivalent or applying it completely. It's sort of a simplified version of the C++ allocator. But then when we get down here, now that I have the memory pool, you notice I'm not doing anything right here. I can rely on the fact that the compiler will add a call to the memory pool constructor for me, right? I will get an implicit call to the default constructor, so I'm good to go. But when I get down to the copy constructor, I know that there is a certain number of nodes I will need, right? If I am copying a linked list that already contains 7 nodes, I know I need a memory pool that can contain 7 nodes. So let's allocate that memory up front. And then I'm just going to iterate over all the source data in my linked list. I'm going to go through every node in that linked list. I'm going to grab the data out of that node, which is what this line is doing. It's grabbing the data out of every node, making a copy of that data, then moving on to the next node, grabbing the data from that next node, copying it, so on and so forth. But that's what this loop is doing. Now, I do realize I am sort of glossing over this range-based for loop and the meaning of const t ampersand. I want you to keep in mind that this is the loop we want to be able to write in every condition. If you can write this loop to solve a problem, this is the loop you want. It handles all the iteration logic, prevents all the silly mistakes. It makes sure you iterate over your data structure from beginning to end. If you can write what is called a range-based for loop, what we have right here, that is what you want to use over a low-level loop. Now that we get down here and we start looking at the destructor now, we can see that the destructor is simplified quite a bit. Because the memory allocation is handled within naive pool, the deallocation logic is now within the naive pool destructor, which is called implicitly from the linked list destructor. Now we can look at the pushback function. We can see instead of saying new node equals new node, I'm simply saying memory pool.getNext. I have replaced the use of the new node. Instead of writing this line right here and simply saying new node, I'm going to use the naive pool, memory pool.getNext. That gives us a pointer to the next node we need to be allocated. Either it's already allocated and it gives us a pointer to it, or it allocates the next block and gives us a pointer to the node we need. And then after that point, the rest of the logic is the same, right? The only thing that changed is how I allocate that new node and where it is allocated. The actual logic of placing it within our sequence of nodes, that hasn't changed. And then the iterator stuff is still the same, but once again, I'm going to defer discussion of iterators until the end of review set 2 and the beginning of review set 3. And review set 3 is really where we are going to focus on iterators and the big 3. Assignment operator, we're still going to use the copy and swap method. And then the swap function becomes a little bit more complicated, namely the fact that we have to add an extra line. If we're swapping 2 linked lists, we can just go ahead and swap the blocks of memory they're using, right? If I have a linked list 1 with 1 block of memory and linked list 2 with a different block of memory, and I'm swapping them, just change who owns what, right? Just do a standard swap, and then we're done. But that's it. Everything else in the swap function would remain the same. So if we compile this and we run it, or if we compile it and we run it, we can see quite a bit happen. So I'm going to go and get rid of all this nonsense right there, and I'm just going to run it normally. And we can see I have some debugging logic thrown in here. The empty case for the allocator, all of that. But what's really happening here is I'm tracing through what cases I have happening in the memory pool. But if we get rid of all of that logic, I should be able to do a 2. I think I want an ampersand. There we go. So earlier on, I talked about how if you're doing debugging output, you want to write it to standard error. This is the line you need to take all standard error output and then redirect it to dev null. Basically, throw away. I do not care about anything written as standard error. Throw it away. I do not want to look at it. Right? Ignore it. And when I do that, I get everything written to standard out. I get everything written to C out. And there we go. And if I want to do this, for example, with 10, 20 nodes, there we go. Or 2,000 nodes, there we go. Versus if I kept all that debugging output, I then get all. But if we turn that back down to something more manageable, let's say we just want 2 nodes. We just want 2 nodes. We can see we get exactly what we expect, right? I create a new linked list of 2 nodes. I create a copy of that linked list. I add a 3rd node to it. I output the original unchanged list. And if I want the debugging output that happens along the way, there we go. And we can see that in this one, I'm getting the easy case, right? I allocate the block up front. I've already allocated the data I need. There is no reallocation that needs to happen. But if I make the linked list larger, I do have to do a couple new subpools. And now we can look at the fun part of this. And then one thing I want you to keep in mind is I'm not looking at list driver, right? List driver hasn't changed. Right? The logic in here is the same. Every piece of logic in here has to deal with the linked list memory allocation. This does not impact anything outside the linked list. This is purely for memory allocation. And the only code that needs to be aware of this is the linked list code itself. The driver, as long as it's calling the copy constructor and push back, the copy constructor is copying data and pushback's adding new data, the rest of the code doesn't care. It is only within linked list in the places I need to allocate the memory that matters. It is only in the implementation details within the linked list itself. Main function, I don't need to know how it's implemented in the main function. Simply that it follows what the documentation tells me it must. Then we get down to naive pool.h, which we can see is also templated. And I'm going to go and set up 2 constructors here. The first is a default constructor where I say, you know what? I am going to upfront say my block size is 8. So every time I go to allocate a new node, I'm going to allocate 8 nodes. And I'm going to start off by allocating 1 such block. So if I call the naive pool with its default constructor, it's going to allocate 1 block of 8 nodes and set the block size to 8. And then you can see a node here. I did initially forget interface completeness. I did forget to write this constructor. Here I'm saying, you know what? Right here, my block size is still going to default to 8, but I need to pre-allocate a certain number of nodes, right? Instead of saying pre-allocate at least 1 node, I'm saying pre-allocate at least some number of nodes I pass in. Pre-allocate at least 1,000 nodes, for example. And then a little bit further down, I have another constructor, which is block size and pre-allocate. This is saying, allow me to specify the block size I want to use, and allow me to specify a block size. Now, you'll probably notice something interesting here. Constructor delegation. So using this initialization list right here, I can say, my naive pool default constructor is going to take these 2 arguments and pass them down into this constructor right here and just reuse the same logic. And the same thing right here. This constructor is going to take 8 and pre-alloc and just pass them down into this constructor right here and let this constructor do the work. This is known as constructor delegation. If I have a constructor that already does the work, delegate the work to it. Which is nice to do. Right? Dry. Don't repeat yourself. If I've already written the logic, and the only thing that changes would be input arguments, the rest doesn't matter. This bracket you see me use, bracket notation you see me using here is initializing a standard pair, which we'll see in a moment. Now, this is a nice modern way of initializing data members for some sort of class type. It does generally boil down to being turned into a constructor at some point. But it is a standard pair, so it's setting the first entry in that pair to first, and the second entry in the pair to second. So next available block is a standard pair in this. And we'll see that in a moment when we get down to the public section of this, go a little bit farther down. Then we get into naive pool right here. So what we're looking at right here, and we will revisit this in more detail in review 3, but this basically boils down to if I want to allocate 1,000 nodes, I'm going to divide that number by 8 and make sure I have enough space, at least enough space for 1,000 nodes in 8 node blocks. And since we know 1,000 is not divisible by 8, we're going to have a few extra nodes. We're going to have a few extra blocks. But we will have at least the space we need. That is a guaranteed invariant, a post condition of this function. And since we have multiple blocks, which we're treating as a pointer to an array of pointers, I'm simply going to say, iterate over all of my memory pool blocks, deallocate each block of nodes, and then once I'm done, deallocate that outer layer of pointers. But once again, we'll go through this in more detail in what's happening in review 3. Get next. This is the allocate function. This is the function I'm using instead of new. And you can see I have kept note of the mistakes I made while I was building this example. But here I'm going to say constant, right? Pool index and block index. These variables, I'm creating these variables simply for my own readability. These variables are not going to change after these 2 lines. I simply created these 2 variables to make it more readable, to make the code a little bit less cumbersome to write. Which is why I've made them const, right? Once I set the values for these variables, I never need to change them again. So let's make them immutable. And maybe the compiler will give me some optimization. Who knows? Then I'm going to go ahead and call the naive pool reserve next function. So this will go ahead and if I need to reserve more data, it will go ahead and handle that. If I need to allocate a new block or something, this will handle that logic. But at the end of the day, I'm going to go to my 2-dimensional array of memory pools. I'm going to pick which memory pool, I'm going to pick which block of nodes in that array. So if it's the 4th block of 8 nodes, I'm going to say, well, I need to go to the 4th block. And the 7th node, the last node in that block, is the next one I need. So if I go down to node, the 4th block of nodes, and I go to the end, I say, that's the next available block. Grab the address of operator, get the address of that last node. And that's going to be the next node I use. Instead of calling new, this is my allocation line when combined with that. Well, we need to have a swap function all the way down, so we need to swap data around. We're going to use the same copy and swap trick to implement the big 3. And now it is very, very important that I implement the big 3 explicitly for this memory pool. But this is all of the public interface. We get down into private, then we start getting to the fun stuff. Reserve next. This is all the logic for allocating more memory and keeping track of what I need. And we can see it gets very, very cumbersome and very, very messy. Now, once again, I said we will discuss this in detail in review 3. So I'm going to defer discussing this in detail until review 3. But there are 3 cases. The case where I already have all the data I need. I have plenty of space. I don't need to allocate any extra data. I'm good to go. So go ahead and stop there. The second case is I'm out of space in my current block of nodes. I need to allocate the next block of nodes. The third case is my array is not big enough. I had 4 blocks of nodes. I need to start allocating a 5th. I need to make space for that. And that is my third case there. But the important thing to keep track of is I sat down and I figured out what my 3 cases were. And I planned it out beforehand. I did not just start mashing on the keyboard when I did that. And then I have a few conditional blocks and a few debug statements in here. Conditional compilation and all of that. And I can turn this on and off at compile time. I can say, I do not want this debug output, and I can turn it on and off at compile time. And all I would do to make that happen is jump into the make file here. Let me go and close. There we go. All I would do to make that happen is I would go into my make file, and this one compilation flag I have right there, I would just go ahead, delete it. And all of that debugging output you see would be disabled at compile time. Of course, I don't want to save that, so I'm going to close that file and discard those changes. And then going through this right here, going down further, then I start getting into, here is my standard pair I was talking about a moment ago. This position pair type So position pair is an alias for just a standard pair of 2ins. The pools is a 2-dimensional pointer. It's a 2-dimensional array. It is a pointer to an array of pointers. Or a pointer to multiple arrays. It's a 2-dimensional array. Then I go down to the number of pools right there. That is the number of memory pools I currently have. Then I go down to blocks per pool, and that is the number of nodes I'm going to have in each block. So if I say 8, the block size will be 8. And then position pair at the end right here is simply a variable, a data member I use to keep track of where the next available node is located. And then once I have all of this, everything falls into place. But I'm going to go ahead and stop here with this one for now. Once again, I do want to remind you, it's just a quick overview of what we'll be discussing in Review 3, and it is looking forward a few weeks.